Welcome to PDC. Today I'm going to be talking about SQL data services and what lies underneath it. The very fact that you guys are here at 8:30 a.m. on the last day of the PDC conference shows that you guys are very much interested in understanding how SQL data services works. I also want to talk about how, I want to give a brief history of how this and how we actually put together this system. Hopefully you guys have already attended some of the sessions that were given by my colleagues over the last 3 days. If you have not watched them or if you have not attended them, I highly recommend you guys to go and watch them online when they become available. The related sessions are SQL Data Services Overview by David Campbell, a lap around SQL Data Services by Soumitra Sengupta, and SQL Data Services Futures by Patrick McElroy. There is another related talk on under the hood talk on scaling out services being given by one of our colleagues, Max Feingold, at 12:30 p.m. today. And I also recommend you guys to attend that. I'm Gopal Kakiwaya. I work I'm an architect at Microsoft. Me and a few of my colleagues who are here and people back in Redmond have worked hard to bring this SQL data services to fruition over the last 3 years. I'm actually a civil engineer. I was born in India, and I was initially trained as a civil and structural engineer. I was always interested in computers and came to US to pursue my advanced education in computer science. After finishing my master's and PhD degrees, I joined Microsoft in 1996 and worked on COM, DCOM, and complex technologies. By 1999, as you guys all know, web has already taken off, in a phenomenal manner. I realized that the websites out there were actually mixing up presentation and logic, and that entanglement was coming in the way of actually having the presentation, the rich clients actually rendering the logic locally, the presentation locally, but accessing services on the web. To address that problem, I played a leading role in creating the SOAP specification that clearly separated the presentation, the markup logic from the actual logic of the service, and leading to what we now call the modern web services. By 2001, I realized that building internet scale services is a non-trivial task. To help ease that problem, I started working on a large-scale distributed system, and over the next 5 years, we developed a number of distributed systems algorithms. We developed them, we worked on them, we refined them, implemented them, reiterated on them, and over the next 5 years, we came up with a system that actually is powering SQL data services today. So this work now is a culmination of a 5-year journey, and for the first time, we are disclosing the details of how this system works in a public forum. And it gives me a great pleasure, and I'm excited to share the details with you guys. Here is my talk outline. I'm first going to motivate, the problems that are solved are addressed by SQL data services. Next, I'm going to describe its architecture in 4 parts. In the first part, I'm going to describe how provide an overview of its concepts, its major subsystems, and how they are put together. In the second part, I'm going to describe how the system achieves high availability. In the third part, I'm going to describe the scalability aspects of the system, like how it scales to hundreds of thousands of databases, hundreds of thousands of users or tenants. And I will also briefly touch upon how we monitor and we deploy and monitor the system. I will describe a little bit the kinds of applications that are built on top of this system, and I will conclude with a slide on the future work. This is a very popular slide. I'm sure you guys have actually seen this slide. SQL Data Services are part of the Azure Services Platform. It has two layers. At the bottom layer, there is a set of foundational services that address the compute management and storage needs of various of the applications built on top of it. And above that are a set of building block services. And specifically, we are going to talk about the Microsoft SQL services in this talk. The goal of our, the goal of our system is to provide database as a utility service. As you guys know, database utility services have pay-as-you-go business model and provide strict SLAs. The consumers of utility services do not care how the system has been put together or how it actually works. They really care that it is available when they need it. I'm going to motivate the three pillars addressed by our service with a scenario. Consider Silverlight streaming, like the recent NBC Olympics. As you guys know, storing video files requires petabytes of storage. Also, cataloging those video files so that they can be instantly searched and detecting copyright infringements on those video files requires a large amount of processing power. It is not enough, to store and catalog video files so that they can be instantly searched. It is also important for us to be able to deliver it, when the user wants to watch the video. You guys might all be familiar with how when Michael Phelps won the 6th gold medal, by razor-thin margin, there was a huge demand for people to watch that particular video clip. So the system should be able to scalably serve content to the end users wherever they are located throughout the globe without any noticeable degradation in latency, even in the presence of flash crowds. And so that's how, all these three pillars are very important if you are thinking of building an internet scale service from a data perspective. Here are the requirements we set out with when we actually started building SQL data services. The scale requirements across all the three pillars is obvious. I don't have to talk a lot about that. We wanted to actually run our service in a cost-effective manner that demanded us to run on previous generation hardware, IDE SATA drives, etc. This introduces a set of problems, and I'm going to a set of problems, and we had to overcome those problems. I'm going to briefly touch upon the challenges we faced when running on commodity hardware in a slide later in my talk. Because we are providing this as a utility service, we need to be also cost-effective from an operational perspective. So that demanded us that our system be self-healing and self-adjusting with very little, hands-on operational maintenance needed. The goal of the system was that if failures occur, we actually don't bother to actually go and deal with it on an emergency basis. The machine fails, somebody every Friday will come and remove the machine and replace it with a new machine, and the system automatically heals when existing machines die and new machines come online. In contrast to other services that you guys might know, we are a database service. That means we have to provide transactional consistency guarantees. So doing that in the presence of failures is a non-trivial task. There can be all kinds of failures in the system. If you think that there's a failure that does not occur in a small data center, I will bet you that it will occur in a large data center. So there are all kinds of failures, hardware, software, and communication failures. And of course, we want the best performance from our system. So I've briefly motivated why and the problems that are addressed by our SQL data services. I'm going to go into the architecture portion now. As you guys know, scaling out stateless services is fairly easy. You put together n copies of your stateless service, and you're almost done. In contrast, scaling stateful services is a lot harder problem. On top of it, if you have to scale a stateful service and guarantee consistency, it is it's even more harder. That forced us to actually solve many of the deep distributed systems problems around failure detection, consistent replication, and failover. And I'm going to briefly describe, how we actually attack those problems. Our system has a lot of moving parts. There are lots of machines that, our system is designed to scale to hundreds of thousands of machines in the long run. There are lots of moving parts, and our system needs to definitely handle all those the different kinds of failures that occur in a typical data center. Our approach has been to use SQL Server, that we actually enterprise quality SQL Server as a node storage solution. Thousands of man years of development have gone into the SQL Server, and we definitely wanted to leverage that as a node storage solution. We didn't want to reinvent the wheel. But I also want to be clear that we didn't actually use off-the-shelf SQL Server bits in our service. We actually took those bits, we modified them as necessary to make them service ready. And so that means we added some components and removed some other components. We added replication into the engine. And certain other things we do from outside the engine, as you can see later in my talk. So we actually use the node, we leverage SQL Server. To tie these SQL servers, which are actually running on any given box, into a cohesive set that self-heals and self-adjusts, we built a technology which we often call distributed fabric. It is this piece that actually solves the distributed parts of the problem. So the SQL Server stores the data that we ask it to store, and it guarantees consistency in a single node. And the distributed fabric is the one which actually orchestrates these SQL servers into a self-healing, self-adjusting fabric, and ensures that failures, the system remains consistent in the presence of failures. And of course, we also have done improvements in automatically provisioning and monitoring our system. So I'm going to provide an overview of the concepts in our system, its major subsystems, and how they have been put together. The first concept I want to introduce is the storage unit. As the name implies, the storage unit is the basic unit of storage in our system. It is the one that supports CRUD operations. Example storage units are a row group or an SDS entity, if you guys have done the hands-on lab. I'm going to use the concepts that you guys might be familiar with, if you have done the SDS hands-on lab, authority, container, and entity. So here is the entity. So at the next level, is the consistency unit. A consistency unit is a set of storage units that can be updated and queried in a consistent manner. Applications typically specify and manage a set of consistency units. And example consistency units are a row group, a set of rows which actually have the same partitioning key or the primary key. It could be a complete database, or it could be the SDS container. The system basically aggregates a set of consistency units into what we call the failover unit, or most often as a partition. It is the unit of management in our system. The whole purpose of the system is to ensure that every failover unit is highly available. Given the fact that applications work at the consistency unit level, whereas the system works at the failover unit level, the system is actually free to split and merge partitions at consistency unit boundaries without affecting the applications. It actually does that to ensure that all the nodes in the system are evenly loaded, or uniformly loaded. This particular slide shows the major subsystems in our SQL data services. At the bottom, as you can see, is the data cluster. All the application data is maintained in a highly available manner in the data cluster. The data cluster is composed of a set of data nodes. Each data node has 3 processes, running inside it. The first process is the SQL server. This is where all the storage happens. The other process is the fabric process. The fabric process and SQL server process are actually tied at the hip. If one of those processes dies, the other process also will die. In other words, their lifetime is the same for all practical purposes. The SQL server processes exchange replication messages. If you actually store, let's say, an SDS entity into a SQL server process, it actually replicates that information to some other processes in the data cluster to ensure that it remains highly available even if after it fails. The fabric processes exchange control messages. In fact, all the failover messages actually happen between fabric processes. And the management services, running inside the management services process, work in conjunction with the service management infrastructure that is shown on the middle left side to actually deploy and monitor, deploy bits into our system, upgrade the bits in our system, and monitor the system health. The right middle diagram shows the master cluster. The master cluster is where we maintain system-wide metadata. For example, what node hosts what partitions is information is a kind of information that we maintain in the master cluster. As you can see, master cluster is composed of a set of master nodes, and master nodes have exactly the same components as the data nodes, but they also host this additional component called the partition manager, which actually is looking at all the nodes in the data cluster to ensure that they're evenly loaded, that all the partitions are highly available, or all the failover units are highly available. So it is actually working in conjunction with the data that it maintains to ensure that the system is working in all the failover units in the system are highly available. The data that is maintained by the master cluster is essentially a cache, because that data can be recreated from the data in the data nodes. For example, what node hosts what partitions, that information can be definitely recreated from the data partitions. We actually maintain that cache because we need to look it up fairly frequently, and we also ensure that that data is also highly available, because in our system any machine can fail at any given time, and we use the same replication and reconfiguration algorithms, the algorithms we use for maintaining application data in a highly available manner, to maintain the master data also in a highly available manner. At the top is our front end, or the front end machines. The front end machines field the SOAP and REST protocol messages. They host the ACE logic. The ACE logic is the authority, container, and entities. After processing, after receiving the message and processing those messages to determine what needs to be done, they access the data cluster via this data access client library. This data access client library is a very thin wrapper over ADO.NET, or the standard ADO.NET DLL. Basically, what it does is, when it receives an operation that targets a particular consistency unit, it looks up its cache to see whether it knows the SQL Server process that is hosting that particular data consistency unit. If it does not find a hit in its cache, it actually goes to the master cluster to find out which the data unit that is currently hosting that particular consistency unit. And after that after receiving the response to the lookup request, it actually forwards the message to the appropriate SQL Server node and receives the response and gives it back to the ACE logic, which in turn processes that response and responds back with an appropriate REST or SOAP protocol response message. I've already briefly touched upon what the service management infrastructure does in our system. It is the one that is monitoring the system, deploying bits into our system as we upgrade the system. In fact, just before we came to this PDC, we actually deployed a patch into our system that actually rolled across about 6,000, 7,000 machines in a matter of 5 hours. And we just did not have to do anything. We just pressed a switch and everything happened. Here is a component view of our system. I'm going to briefly describe each of those components, as in the later part, as we progress through my talk. The important point is that, as I've said, our system at the back end, when we go down to the underneath our system, the system is actually maintaining the failover units of the partitions in a highly available manner. In order to ensure the high availability of each partition, it places each partition across, across multiple nodes. And it ensures that the replicas of a given partition are actually span many failure domains. Like they are not all placed in the same rack. They all do not share the same switch. So even if we see a single entire rack failed because somebody pulled the switch or somebody pulled the network cable from a switch, our system remains highly available because these partitions actually span those failure domains. So here, the blue partition got placed, and its primary is in data node 102, and it has secondaries in nodes 100, 101, and 103. And the yellow partition got placed with the primary replica in 103 and secondary replicas elsewhere. And as you can see, as the system builds up, it actually starts placing the partitions across nodes so that all the nodes host roughly the same number of partitions so that they are evenly loaded to begin with. Why do we actually make the system, each node host multiple partitions? There are 2 reasons. One reason is that if a node fails, its load can be now distributed to the rest of the remaining live nodes in the system. So a single node failure gets distributed evenly across a bunch of nodes in our system. When we want to build a replacement node to an failed node, again, we need to build it very quickly when we decide to build it. That means we can actually suck the data for the partitions that are going to be hosted by the replacement node in parallel from different parts of our network, different parts of our data center, because they come from different source data nodes. So this allows us to build, handle node failures and node rebuilds in a nice manner. So this is a small recap. So basically, we have 2 kinds of failures, 2 kinds of nodes, the master nodes and the data nodes, and the system, detects failures reliably. The important point I want to stress here is that the local failures in the system are treated as fail-fast failures. In other words, if we detect disk corruption, or if the log becomes full, the traditional database administrative tasks, do not cause any system-wide outage in our system because we immediately take that node offline. And so local failures always, cause the node to fail fast. Here is a slide. These are all the things that we actually encountered in our system while we were running the system. As an example, we had this faulty NIC in our system. What it was doing is that you give it a message to be sent from point A to point B, and it would actually take the destination MAC address, put it right into the middle of the packet, and then compute the TCP checksum. So the receiving node will actually verify the TCP checksum as valid. And then when we actually try to parse that packet, we would see this failure. I mean, we would see parsing errors. We never could understand what was going wrong, and ultimately we located that to be the faulty NIC. And in order to, and it was a terrible thing for us to go and debug. So in order to prevent us from having to deal with this, we actually sign every message that flows through our system, whether they are replication messages or the control messages related to failover and other things. And we also observe bit flips on the disks. And so we actually enable page checksums in our SQL Server process. And SATA drives do not actually honor the write-through command that we give it. I mean, we say, hey, so we actually periodically go and flush the cache. So there are a number of challenges that one has to overcome, and here is a flavor of those challenges when dealing with commodity hardware. So I've finished the overview of our system. I'm going to briefly describe how the system achieves high availability. Before I talk about how the system maintains data in a highly available manner in our system, I have to first describe how the system actually detects failures in the system, machine failures in the system. As you guys know, failure detection is one of the fundamental distributed systems problem. Solving that allows you to solve consensus, which allows you to solve other problems, other consistency problems. In our system, every node is assigned a unique ID. This unique ID is either a SHA hash or an MD5 hash of, for example, its machine name. That makes the nodes actually get randomly distributed in the ring. Each node maintains information about its successor and predecessor node, and that's why we get this topology, this ring topology. The rings are bootstrapped by a set of seed nodes, and a new node joining. I will describe how any new node joins this ring in the next slide. If you actually look at this slide, it actually shows you a snapshot of the system at some point of time. The ring is never static. It always keeps changing. New nodes, as new nodes arrive, they have to join their appropriate position in the ring. As existing nodes fail, they have to be removed from the ring. So the ring is under a constant flux, and what you're seeing here is a snapshot of the system at some point of time. As you guys know, it is extremely hard for a given node to know all the other live nodes in the system. In fact, it's impossible, because the node might have just joined the system, and it's impossible for it to know all the other live nodes in the system. So what it does is that each node maintains a tight knowledge of its ring neighborhood and maintains routing partners at an exponential distance from its ID. What this allows us is that any given node can reliably locate any other node in the system by using a distributed routing protocol, which essentially is a distributed binary search. In addition to maintaining knowledge of its ring neighborhood, each node claims ownership of the ID space, which is starting with a midpoint between its ID and its predecessor node ID, and ending at the midpoint between its ID and its successor ID. For example, in this particular slide, node 64 has knowledge of nodes 83, 76, 50, and 46. It owns the ID space between 57 and 70 roughly, and it maintains the exponential routing partners that are shown in the slide. If the node 64 wants to send a message to a target ID 118, it basically looks up its routing table, finds out the node that is closest to that ID, and sends the message to it, in this particular case, node ID 135, because that is the node it knows to be closest to 135. 135 in turn forwards the message to the node that it knows to be closest to 118, which in turn forwards it, and it actually terminates at node 120, because node 120 at that instant of time actually owns the ID 118. If you actually look at this in the ID space, the linear ID space shown at the top of the slide, you can see that it's actually doing distributed binary search. That means that the search for any given node in the system is guaranteed to terminate in logarithmic hops. It doesn't mean that we incur the logarithmic hops all the time. These nodes actually aggressively cache the presence of other nodes in the system, and only when it does not know the existence of a node in the system does it actually incur these routing hops. So most of the time, they are single hops. This particular slide shows how the ring heals. Self-heals and self-adjusts. At time t0, as you can see from this slide, the ring neighborhood of node 64 is 83, 76, and 50, and 46. At time t1, nodes 76 and 64 failed, and a new node arrived. The failure of nodes 76 and 64 will be detected by the nodes 83 and 50 because they're monitoring their neighbor nodes. After detecting those failures, they would start attempting to claim ownership of the ID range spanned by the failed nodes 76 and 64. While they are trying to actually claim the ownership, a new node arrives, and we go through a complex protocol, joining protocols, and at time t2, the system again comes back to a steady state with the ring neighborhood around around the failed node 76 and 64 and the newly joined node 61 as shown. At this point, the failures are detected, and the system reports the failure of the node 76 and 64 and the arrival of the new node 61. So we now understand how we actually detect failures in the system. When a machine fails, we actually can tell when the machine has failed. That actually solves only one part of the problem from a data availability perspective. We have to solve the other problems with respect to maintaining the data in a consistently highly available manner. So how do we achieve this? So a well-known technique that we all know to maintain data in a highly available manner is to maintain multiple replicas for that particular data. Each of the replica has to maintain the data in exactly the same manner, otherwise you would lose consistency. That means all the incoming client operations need to be linearized into a total order, and each replica has to apply those operations in that total order. In our database community, we also sometimes refer to this as serializability. And once an order has been established, that order cannot be changed because otherwise you again will lose consistency. So the way we achieve this is by maintaining that linearized order, by establishing that linearized order at a distinguished replica called the primary replica. So all the client operations go to the primary replica. It establishes the order and forwards those operations to the secondary replicas, which actually apply those operations in that specified order. And then the client actually receives a successful acknowledgement when a number of them have actually committed that operation, which I'm going to briefly describe. I'm going to briefly describe how we accomplish replication in our system in the next slide. The important point is it is not enough to just replicate all the operations into a replica set. As you guys know, it is guaranteed that over a period of time, every replica will fail. If you allow sufficient amount of time, replicas are guaranteed to fail. And the system and that particular failover unit being backed by that replica set will become unavailable. So it is important for us to detect failures, and after we detect failures, we need to replace the failed nodes with new nodes so that the replica set actually operates at close to the desired capacity all the time. And that requires us to reconfigure the replica set when we detect failures. So these two protocols have to go hand in hand. The replication protocol and the reconfiguration protocol have to cooperate to ensure that the linearized order that has been established by the previous primary continues to get honored as the replica set undergoes a series of reconfigurations to go from configuration A to configuration Z. So how do we accomplish replication? In this particular slide, I show a replica set of 5. There's a primary replica, which is a distinguished replica. There exists always a primary replica in a replica set in our system. And it is the one that receives all the operations, client operations. Let's say in this particular case, I'm showing what happens when we do a read. So the primary replica receives the read request, and it immediately responds back. It does not have to talk to anybody because it is guaranteed to have the state that is needed to service that read in a consistent manner. Note that we actually always guarantee consistency in the system. If, on the other hand, if it's a write operation, the primary replica receives that write operation, forwards them to all of its secondary replicas, and when a quorum of them acknowledge back, in this particular case, the write quorum is 4, it actually responds back to the client saying that, hey, I've committed your transaction. Your transaction is, your data is now highly available and durable, and it is guaranteed to be consistent. And then the one of those secondary replicas, which actually, was maybe incurring load on other partitions that are held by that particular node hosting this particular replica, eventually will come around to acknowledging the client operation that was forwarded by the primary replica back to the primary replica. At this point, the primary replica says, oh, I've already acknowledged this client operation back to my client, so I don't have to do anything, and it is done. The important point here is that if you can see that we are not, modulo the reconfiguration protocol, which I'm going to describe next, the order of operations is always the same there between the primary replicas and the secondary replicas, because the primary replica is the one which is establishing the order, and the secondary replicas commit those operations in that same order. Another important fact is that in our system, the actual operations that are replicated by the primary to the secondary are not the client transactions. The primary receives the client transaction, and the primary processes that client transaction and determines the rows affected by the client transaction. So the actual operations that are replicated by the primary to the secondary replicas are the rows, affected rows. After replicating all the affected rows, the primary replica actually sends a commit operation to the secondaries, and the acknowledgement by the secondaries is for that commit operation. And when a quorum of secondaries actually acknowledge back to the primary that a particular commit operation has been completed, the primary actually responds back to its client stating that, hey, your transaction is now complete. Okay. So as I've already said, the replica set needs to be reconfigured when node failures occur. Otherwise, the replica set will become empty over a period of time. And the way we accomplish that replacement of failed nodes with new nodes, or removal of failed nodes, is via this protocol called reconfiguration. So there are different kinds of reconfiguration. The most important one is, of course, the primary failing, because when the primary fails, this replica set is no longer available. So all client transactions actually start seeing failures because the primary has failed, and they cannot send the transaction to anybody else. So the system immediately detects that the failure of the node, and then promotes one of the secondary nodes as the new primary. And now at this point, the replica is, the failover unit that is being backed by this replica set is operational again. This other kind of failure is removing a secondary that has failed. That can actually be done in a leisurely manner, because we hope most of the times nodes, when they fail, sometimes they come back up because we periodically reboot nodes. Like, for example, in the case of patching, where we are doing a rolling upgrade across a series of machines, a set of machines go down, the patch, they reboot back, and then we reboot another set of machines. So when a secondary fails, we just remove it from our replica set, and the replica set is still highly available. The reason we remove a failed replica is for performance at this point, because the primary continues to send its operations to that failed replica, which of course do not get acknowledged. So nothing happens. We tell the primary that its secondary has died, so that it stops sending those replication operations, which are not going to be ever acknowledged. So at this point, the node that actually failed actually comes back. Let's say it got rebooted, and the patch got applied, and it comes back alive. So it comes back alive into the system, but at this point we say, hey, there's already a working primary. I don't want to disturb that primary. So we add the replica that was a primary in the previous configuration into the current configuration as a secondary. some time elapses, and the system says, oh, you know, the desired replication factor for this replica set is 5, but it is operating with 4 replicas at the moment. So I need to build another replica for this particular replica set. And that process continues while the partition is actually, while the client is still, while the primary is still accepting client operation. So we build it on the side, and when the build, because remember, there could be gigabytes of data that we need to transfer from this replica set into the newly built replica before it actually becomes part of the replica set. So we do this build on the side, and when the build is fairly complete, not much needs to be done, we bring it back into the current configuration as a new secondary. At this point, the replica set actually is back to working at the desired replication factor, and all the failures have been accounted for. So this is how our system continues to maintain high availability in the presence of all kinds of failures, and also ensures that the order that has been established never gets disturbed. So this reconfiguration protocol, of course, needs to be safe in the presence of cascading failures. You know, the failures can cascade, and it assumes the presence of a failure detector that I've already described, and assumes a leader election algorithm for electing the primary replica. So I've briefly described how the system achieves high availability. I'm going to touch upon the scalability aspects of our system. So as I've already described, you know, the partition manager is the component that is responsible for maintaining all the failover units in a highly available manner. It is the one which is responsible for placing replicas across failure domains, ensuring that all the failover units have the desired replication factor. It is the one which watches the system and ensures that all the machines in the system are uniformly loaded. If they're not uniformly loaded, it induces load balancing. It takes load balancing actions. That may involve actually splitting a partition into 2 different partitions if one of those partitions is extremely hot. So partitions can be split until it ends up with only one consistency unit. And if that consistency unit is hot, at that point we cannot actually move it around without doing something, and without raising alerts and other things. And telling the client which is hitting that particular partition to look at its logic and understand why it is doing it, why it is making that particular consistency unit so hot. I've already described how we assign multiple partitions to every node in the system. It makes it easy for the system to handle failed nodes, because the failed node load gets distributed across a set of live nodes. And it also allows us to rebuild the replacement node for the failed node very quickly. This particular slide, basically, it's kind of like a workflow slide which shows how the system comes up, starts operating, and handles the failures, and then continues to operate. So in this particular case, let's say the system just came up. As the system comes up, partitions get placed on the nodes. As you can see, partitions get placed across failure domains, and it ensures that all the nodes get a fairly uniform distribution of partitions initially. So, every partition has the desired replication factor, and the system, and all the partitions have been placed, and the system continues to operate. At this point, one of the node fails. As I've described earlier, the failure of that particular node is detected by the node adjacent to it, in this particular case, node 104, and it sends a message to the partition manager, hey, one of this node failed. This partition manager now goes and looks up at the global partition map, which tells us which partitions got affected. So given a node, the failure of a node, it knows what partitions that were hosted by that node were the primary partitions, and what partitions hosted by that node were secondary partitions. Of course, as I've already described, if a primary node dies, that particular partition is not available for client operation. So we need to quickly reconfigure that particular partition so that it becomes highly available. So the partition manager, after looking up the global partition map, determines the primary partitions that were affected by the failed node and informs one of the nodes, in this particular case, hosting the partition that got affected, to become the primary for that particular partition. So as you can see, now that particular partition is operational, but it is operating with a replication factor of 3 instead of the desired replication factor of 4. By the way, in our system, we actually run with a replication factor of 3, though these slides actually kind of use different numbers. And after a period of, after some time, it knows that, hey, it needs to go and inform the primaries of the partitions whose secondary was placed with the failed node, that they no longer have to send their replication operations to the failed secondary node. So in this particular case, the blue partition and the pink partition got affected by the failed node, and so the partition manager goes and informs those nodes that they need not send the replication operations to the failed node. So now those guys stop sending the replication operations to the failed node, and then once again, these partitions are working with the replication factor of 3, even though the desired replication factor is 4. At some later point in time, the system says, okay, this failed node is not coming back up, so I need to place these partitions elsewhere, and it does that by distributing by building those partitions at different nodes. This is how the failure of a single node the load of the failed node get actually distributed across a set of live nodes in the system. In this particular case, the failure of the node 103 is picked up by nodes 101, 102, and 104 because it hosted 3 partitions. And once again, every partition is now working at the desired replication factor of 4. So I talked about how partition manager is an essential component in our system. It is the one which is actually maintaining the global partition map, which is an important piece of information, not only to tell the clients that are the target primary replica for a given consistency unit, but also for ensuring that the system is evenly loaded, and ensuring that all the partitions are highly available and working at the desired replication factor. So the partition manager in this particular case is operating, and it continues to operate as long as that node is alive. But as I've already described, any node in our system can fail. So what happens when this particular node fails? And this particular slide shows that. If that node has failed, once again, our system detects that failure, and then it basically needs to elect another node, to become the primary master. But in the case of data partitions, it is the partition manager that is making that decision. It says, oh, what are all the affected nodes? And from those affected partitions, it says, oh, I need to elect a new leader for these partitions. And those guys actually go and do the reconfiguration, and the system becomes operational again. But in the case of master, there's no such guy. And here the fabric comes and says, okay, the node that is holding the ID token for the ID 0 is the node that actually will become the primary master. And so the fabric plays a leader election role for making the master partition highly available. So in this particular case, because a previous node died, which had an ID of 10, the next node that is going to pick up its place is node 250, and it becomes the primary master. The fabric now actually told it, hey, you're the leader. So that is that leader election module. It is telling that node, hey, now you become the primary master. And this guy now actually uses the same replication algorithms and reconfiguration algorithm to reconfigure this global partition map to ensure that it is back to its consistent state. Because it was a secondary earlier, and it got promoted to the primary. That means it may have missed some operations, and it needs to ensure that those operations are back. It catches up to those operations. And now this master is again alive. So as you can see, in our system, we don't have any single points of failure. The system continues to self-heals and self-adjusts, and all the every service is actually highly available. So let's have the questions at the end of the talk. Let's have those. I will answer the question in the question and answer session. So come back to the mic, and then that way it gets recorded and people can. Okay, so I've kind of described how the system handles a large number of partitions and consequently the large number of databases and the users. So I'm going to briefly, in this particular slide, I'm going to describe how at a very high level, how the system self-monitors itself, how we deploy bits and upgrade bits in our system. As I've already described, each data node has a management services process in which we host a number of components. For example, there's a watchdog component which is looking for, hey, how full is the disk log? How full are each of the logs? So they upload this information into a service management infrastructure, which I've actually shown earlier. And this aggregate view is very useful for us because we actually look at the state in the device manager to understand how the system is behaving in a coarse, at a highly coarse level. Of course, all the detailed information is actually maintained in the data nodes. We don't want to upload everything into the service management cluster. We only upload aggregate information there, and it only maintains aggregate information. When a deployment happens, when you bring in a new node into the system, the deployment happens via the deployment components. These are the ones which suck the new bits, apply the patch, reboot the machine, and things like that. And we upload periodically. We have another cluster in our system called the perf collection cluster. We periodically upload, hey, the number of client transactions that are being incurred by all the partitions hosted by this particular data node. That gets uploaded into the perf cluster. It gets uploaded into a database, and we actually run analytics on it to understand, hey, how did the system behave over a period of time? Do we need to do something better? And if there is any bug or if there is a failure that we really do not understand, we actually go through the trace database and go through to understand what happened in the system. Using the traces, we can actually thread how a given client transaction actually flowed through our system to understand what actually happened at every step of the way before that failure occurred. And of course, we have the backup component, which can also do offsite backups. So that actually concludes the architectural part of my talk, and I'm going to briefly touch upon the different kinds of applications that we have built on top of this system. The first system is something that you guys should all be familiar with by now, which is the SQL data services. As I've said, it has the front end and the back end. I've mostly described the architecture of the back end in this particular talk. The front end is a set of stateless, is essentially a stateless service. All its state is maintained in the back end. So it is composed of a set of stateless boxes, and they host the three components that I've already described: the protocol head, the actual ACE logic, and then the access library, which they use to access the back-end databases, the back-end clusters. Another application that is built on top of this infrastructure is the Velocity. Some of you guys, I don't know how many of you guys have actually attended the Velocity talks. So it actually uses the same infrastructure, in fact, the same algorithms for achieving high availability. An example usage of Velocity is to maintain the ASP.NET session state. Today, the ASP.NET session state can either be placed in a database or in a process, but it's not highly available. But using this infrastructure, we can make the ASP.NET session state highly available. For that matter, any distributed cache, any data that you put into Velocity, distribute Velocity. Here is the work that we still have to do. We are actually working on actively as I speak. One is our backup and restore is still working at a very coarse granularity. We need to improve that and to make it much more incremental. We still use, so today we actually use all the updates to a B tree go to the same B tree. We are exploring opportunities to actually improve that by using differential B trees. In other words, we actually seal a particular B tree, and all the updates go to another differential B tree, and then the lookups actually have to be also properly modified. What this achieves is, more reduces the random I/O on the disks. And another thing that many people come and ask us is, hey, you're giving us this notion of consistency unit, but each consistency unit can only be very small. I mean, maybe up to a gigabyte or maybe couple of gigabytes. What happens if I actually have to span my transactions across consistency unit, and I want those updates to be consistent? We only guarantee consistency today within a consistency unit, and that forces us to go and solve the distributed transactions problem. Note that I'm not talking about the traditional two-phase commit problem, because that won't scale in our system, and also it is not resilient to failures, because if the coordinator blocks, a two-phase distributed transaction actually blocks. We need to come up with schemes, or we are working on algorithms to make the distributed transaction also to be highly available and reliable. We are working on Joe replication infrastructure, both synchronous as well as asynchronous. In the case of synchronous replication, we actually place the replica sets across data centers, so that even if entire data center goes down, you actually have your data available, and it is guaranteed to be consistent. Of course, you have to pay it's costly, because all the replication operations now cross data center boundaries. But if there are certain cases where that is a request that we heard from our customers, like financial transactions. There is also an opportunity for us to do the asynchronous replication. In this case, you have the replica sets in two different data centers. Each replica set is independent, but they actually synchronize data in an asynchronous manner. It could be that one of those replica sets is the primary replica set and the other one is a backup replica set, or they could be independent replica sets, in which case we need to use the sync technology to actually make sure that the conflicts get resolved. And another thing is the distributed materialized views. Today, you as end users have to choose the partitioning key in your application, because as I've already said, each application maintains a set of consistency units, and each consistency unit is partitioned using a particular key that the application decides what to choose. That the application decides. What happens if the application wants to look up its data on a different key? For example, let us say all the data is partitioned by purchase orders in the triple of customer purchase order and the line item table. If you want to look at, and so given a purchase order, you can easily locate it and you can do all sorts of things. But what if you want to also locate all the purchase orders placed by a given customer? In this particular case, one option is for you to go and hit all the partitions where that particular customer data could be located and actually build that information. On the other hand, we can actually build this in an asynchronous manner and maintain it as an index, as a separate index, distributed index in this particular case. But it's not guaranteed to be consistent with the primary index. The primary partitioning here is the purchase order partitioning, but we can actually maintain other views on this particular partitioning, which actually partitions data in a different way. We are actually working on the processing framework so that we can actually process huge amounts of data in a failure-resilient manner. We can store the data, but we also need to process the data, and of course the associated distributed query work. Okay, so that concludes my talk. The evals and recordings, please go and evaluate the session and the Q&A. So, thank you. So before we go into the question and answer session, I want to run actually one simple test for you guys, which is something that one of our colleagues here has written. So basically, I'm hitting our internet service with a set of requests, and when this test completes, we will understand the network characteristics of accessing the service from out in the internet. With that, let's go back to our question and answers.
During the session, you mentioned about the recovery of the nodes, replacing a primary, replacing a secondary. In an active system that's receiving updates continuously, how do you determine what delta of information to apply back to the secondaries to bring them up to date?
So as you know that there is a total order that the system actually maintains. Of course, that gets checkpointed, but at any given time, each operation, each client operation is assigned a log sequence number or a logical sequence number. So when during reconfiguration, we determine how far or how different each replica in the replica set is. So we determine, this particular, we need to, if two replicas exchange that information, we know which one is more advanced and which one is behind. And they exchange only the delta so that they all get caught up to the same LSN.
So you have custom processes for reading the logs to determine that?
Yeah,
delta?
so that's what I said, right? We actually have replication components inside the engine. That is the functionality that we added back into the SQL server to go and read the logs and then process those logs.
Okay.
And this is all done at the runtime, so it's not actually going and hitting the disk. It's all in memory.
Yeah, hi. Enjoyed the session. It's this under-the-hood topics of the physical aspects are very interesting. It looks like you're very committed to it. I haven't seen all the sessions, but there's a whole other set of under-the-hood topics that I was interested in, which are the bits that have been added and the bits that have been removed to the RDBMS capability. We were in the Ask the Expert session last night, and Tudor, I don't know if you know him, but he was our expert at the table. And we kind of came to the conclusion that even SQL data services is a misnomer because of the subset of SQL that is actually implemented. You know, there's a subset of data manipulation language. There's no data definition language, et cetera. And it's those things that I'm kind of interested in to understand what the capability is and what it's going to be. He had also mentioned at the time that it's really a kind of a vSAM btrieve architecture as opposed to an RDBMS architecture. So those are the types of things that I'm trying to understand. Apparently the data may be stored in like a fifth normal form, such as a SharePoint implementation. Those are the kinds of things that I would like to know under the hood. I don't know if there's another session that addressed that, but those are really critical things for me. You're working with a node that's, you've got the logical node there at the top of the tree, and you're handling all the ILTs, which is great. I'm kind of curious about what's in that logical node that's under the hood.
Okay, so as you can actually see from this talk, we have the full capability of the SQL Server available at the node. For example, if you actually go through our data access layer, you actually have full SQL functionality there.
Okay, well, I'm sorry, stop. I'm sorry, because again, there's data manipulation language is not implemented at all. Create table, alter table, et cetera. I mean, ANSI SQL is just absolutely not implemented as of today.
No, right? That is what I was about to say.
Okay, sorry.
I was just trying to say that you can see the latent capability in our system at the front end machine. From the front end machines, when you're coming via the internet, we chose not to expose the underlying database functionality. But this is the first iteration of our service. We wanted to start with something simple. There's a whole community out there that is that loves the model that we have today, which is this flexible entity model. You don't have to define the schemas. You can add any type of entity that you want. And there's a whole other set of community out there to which looks like you belong, which really wants to have the SQL functionality exposed.
Well,
we will, over a period of time, expose more of this functionality. It's a question of us, opening up the tab a little more. So the underlying latent capability is there in our system.
Right. Yeah, it's just that, sorry to interrupt, but now I was in one session which was on performance implementation, and what was described in that session, for example, was to use many containers and map them across different nodes so that so the query would be distributed, which is describing something very different than a clustered RDBMS structure. So okay, if you're saying it's going to eventually be a clustered high-performance RDMS structure, great. What I was hearing in that session was something totally different, and should we be planning for some type of parallel distributed data management?
Actually, if you really care about performance, even in the case of a traditional database, you really have to spread your load across multiple spindles. Now think about you actually spreading your load across multiple machines because no single machine can hold all your data. So I don't think the performance characteristics that were described in the talk are orthogonal to the fundamental capability that we have in the system. The fact is that you really have to think when you are building a large-scale application. If it's an application that can fit in a single node, then it's no problem because you will go to that node and you have all the functionality that you need. But if you're thinking about a large-scale application, you really have to think about your partitioning mechanism, how often you are accessing the data across those partitions. We will give you the capability to do distributed transactions in the future, but that would come at a cost. It would not be as cheap as accessing data in a single partition. So you really, as an application designer, really have to think, hey, what am I doing? How am I partitioning our system? How often am I accessing data across partitions? I don't think that need will go away, at least in my opinion, for a long time.
Thank you.
Your distributed fabric appears to have many features in common with Oracle RAC. I was wondering if Microsoft was considering putting some version of the distributed fabric in a future release of SQL Server.
Actually, the answer, I mean, there's a product that Microsoft is going to is actually working on. But I do not know when and how that actually will come to the market in the near future. But I do want to say that this particular infrastructure is a shared nothing architecture, whereas Oracle RAC is a shared disk architecture. So we fundamentally will scale much better. At least that's the premise on which we are working on this system. But I cannot comment on when we will actually produce a competitive response to Oracle RAC. But I believe, I'm pretty sure it's being actively worked on.
Okay, so quick recap, if I'm understanding correctly. So the container is the method of partitioning, and I choose that based on my application. Container then maps to a replica set. All reads go to the primary replica. So that means the container, I need to make sure that my container is sized to how much reads, if I have a read-intensive application, that a single replica can handle. How do I think about that? How many can it handle? How do I know whether or not I've partitioned correctly? How much, whether or not I've got the right level of granularity on my container? So
that's a good question. So at any given time, if you have to make sure that the consistency unit can handle the kind of load that your application is wants to is the kind of load the application is actually expecting. So all the reads get actually satisfied at the primary, and those reads are consistent reads. So if you really don't need the consistent reads, you can actually cache that data elsewhere and then actually service the reads from there if your load is read intensive. Of course, if you really want your reads to be consistent and load extremely hot, then you have to pay for it.
Right, but how do I tell, right? I mean, how much, can you give me a rule of thumb, right? Can I do, obviously it'll depend on the type of queries, but is it 100 requests per second? Is it 1,000? How do I know that I've scoped it correctly?
Oh, okay, so we actually expose a set of metrics at the consistency unit level that you can actually get and say, hey, here is the number of operations I'm doing on it per second. Here is the latencies I'm seeing on that. See, remember the system beneath is actually trying to load balance it, and eventually it will come to a point where that particular consistency is so hot that it kept it in, that is the only unit that is on that particular node. At that point, you will start seeing that is the best the system could do, and at that point, you have to change your application.
But how do I know that I'm at that best point, right? Do I have visibility into how many other nodes?
The metrics will tell you that.
The what?
The metrics. So if you actually
tell me that I'm the only container on that node at the time.
Eventually they will tell you that. Eventually it will tell you that, hey, this is the best the system can do for you, and you have to really change your...
Okay, so there's a message or something in there?
Yeah.
Okay, thanks.
Sorry if I missed this, but when the front end is taking, write queries and going against the back end, and the primary data node fails and it has to be swapped out, it may miss some of that. Is there any implied queuing or persistence at that front end, so that those transactions or those writes can be, or those queries can be reapplied against the back end? How does that work?
Yeah, so the front end, when it sees a failure where sees that the primary has died, it actually retries those operations for a few times by holding on to them. But eventually it gives up and then tells the client saying, hey, retry this operation, because it can't keep holding that state in the memory. And as I've already said, that machine may die, in which case the application will face that will get the error anyway. So the applications should be anyway resilient to receiving these kinds of failures. So that's why updates, you can use optimistic concurrency updates when you're coming via SQL data services.
Okay, thank you.
So you can make them idempotent.
Thank you.
If this technology is not going to surface soon for on-premise deployments, are you going to publish some kind of white paper or maybe more detailed reference architecture that we could use to achieve similar results?
This is a frequently asked question. People want this same infrastructure on premises too, and the Microsoft is actually really thinking about actually providing these kinds of infrastructure on premises. One of the fundamental tenets of Microsoft is that, hey, we provide you a set of capabilities. You can actually choose to actually have us host those services in our data centers, or you can actually host them in your own data centers. The exact timeline I cannot actually comment on, but it is something that the Microsoft will actually do. And of course, we will definitely publish a series of white papers when that happens.
Okay, thank you.
SQL Server 2005, you have things like dynamic management views for getting some metrics on performance, and I'm wondering today or how soon in the future are you going to have APIs where you can call in and get some performance metrics so that you can tell what's going on with your application on the system?
So you already have a flavor of that. If you actually do a get on the container, you actually get a bunch of metrics from the internet. Of course, those metrics do not look anywhere close to the metrics that we actually have available on the back end. And it's our desire and a goal to expose more and more of that information. The logical aspects of the system, we want to actually allow the user to be able to control. But the physical aspects we want to hide from him, because we don't want to we don't want him to think about, hey, I need to share my log across these databases. So those kinds of things we want to hide. But most of the logical aspect we do want to expose, and it is our desire to expose it. And you have a flavor of that already by actually doing a get on the container. You would actually see the matrix.
Yeah, I'm pretty familiar with performance stuff, and I know that's a real tough problem. So I'm going to be real interested to see how you are able to roll out new features, because I can see how if you rolled out all the features in the SQL, T-SQL, you'd have a performance nightmare.
Yeah.
So it'd be interesting to see what subsets or how you're able to do that so that people don't have queries that come in that do terrible things.
That's exactly the reason why we are not exposing anti-T-SQL today, because we want to learn and understand, and we want to walk and run. So we want to understand how the system performs under the simple for the simple protocols, and then we actually want to progressively open up the functionality. So I would be glad, for us, we probably should exchange, and you can send us some emails or something like that for the kinds of data that you want to see exposed.
One last question. Given that you have this experience with these large systems, and I'm kind of curious as to what the failure rate is that you observe in practice, and what kind of failures in terms of, is it hardware failures really, or is hardware fairly stable, or are you really seeing software failures? What kind of failures and what kind of rates are you seeing on these large conglomerations of servers?
Actually, that's a good question too. Of course, there are software failures and the hardware failures, and the typical software failures are bugs in the system, and hopefully as the system actually matures, those bugs get weeded out. And there is a random distribution there with respect to software failures. Sometimes it could be that we are not handling a particular message well. Starting from that, then there is the hardware failures. Of all the hardware failures, the most common one is the disk failures. The disks really go down badly. So in order to, of course, that's why we fail fast that system, and we replace that with a new node, and we proceed. The next common set of failures after the hard disk failures are the motherboard failures, the memory failures. And so we do see quite a bit of hardware failures, and it is also surprising the amount of network failures you see in the system. The network switches run really complex software. It is quite amazing how often they drop packets, how often they flood the networks. And most recently, we had a switch that actually is flooding constantly messages into our system. And those are the guys, they also do happen. So we have seen a range of failures. The most common is the hard disk failures, motherboard and system failures, and then network failures. That's the way I would characterize them. I would also guarantee that any kind of failure that you expect not to occur will occur in these kinds of systems.
You mentioned that you are using a customized version of SQL Server, or that you have used SQL Server's code base for your database management system. Are you able to reveal something about the OS and the hardware you are using?
Oh, actually, yeah, of course, we don't actually touch the OS. We are in the SQL Server group. Of course, if you actually look at that Windows Azure, they are actually modifying the OS as well to suit and to make it more friendly for the data centers.
So you're running on top of a modified
version? No, we are running on
Windows?
plain vanilla Windows 2003 at the moment, and we are in the process of upgrading to 2008.
Okay.
Okay, I'm going to show that thing that one of my colleagues has written. Yeah, it has completed. Okay. No, nothing to debug here. So let me run it again. Tony? So this is something that he has written, and I wanted to show it to you guys because he worked hard. Yeah. He hasn't finished? No. Yeah, he hasn't finished yet. So it's pounding on that service, and then it will come back up.
So is this understanding correct? When you're using the flex entity model, the basic way to define the partition is the container, and that's the only way? Or is there any other concept of partitions? Like you talked about purchase order as your partition key. Is the idea then that the designer who's designing the set of containers factors that in? Can you talk a little bit about?
Yeah. So each application is free to choose any number of containers, and it has to think about all the operations that it actually does within a container and where it needs consistency in determining what its ideal consistency unit semantics are and how many of those containers one needs. So it is up to the application to decide the number of containers and how many of those it needs and how many of each of those types it needs and the number of types of the container. So it's definitely in the application design space.
And that's totally different than having a table and deciding on a particular key as your partition key. For example, in the underlying Azure services table model, when we went to those talks, they talked about, yes, you've got the notion of a partition key. If you do have in one of your flex entities a key that you think of as a partition key, that's still something that you have to factor into the design of your containers. That's not something that the system picks up on or that you declare to the system.
No, because it's definitely an application semantic.
Yeah, okay.
Even when you're when you're partitioning it by the key is being defined by you,
Yes.
and you're defining the granularity of that partitioning, even if you're working at the table
Sure.
level.
Yeah.
So
it's just a different data modeling.
Yeah, it's just a
paradigm.
different data model. If you're working at the flexible entity level,
Right.
you still have the same partitioning mechanisms, and you still have to think about that partitioning.
Right.
But
Yeah.
you know,
From the perspective of us as application designers, if you transition in the future to supporting more capabilities, to us it would be an entirely different system, because the way you think about it from a data modeling perspective would be different.
Yeah. So, of course, there is, as I told, there is the world which loves flexible systems
Yeah,
and
sure.
flexible entities, and
Yeah.
this world that loves the schematized table model.
Yeah.
And we want to support both.
Right.
And, unfortunately, today we are starting with the flexible model. But
Yeah.
over a period of time, we would support more and more of the capabilities that underlie our system.
Yeah. Thank you. Yeah. 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 Okay. Okay. Thank you.
Okay, one final question, and I
Just
have
a
to
quick
conclude.
question. Could you tell us in what language or what languages it is written on the percentage? Is there any .NET in there or pure C++?
Oh, so entire SQL Server is written in unmanaged code. I mean C++. The Fabric process is all written in managed code.
Okay, great, thanks.
Thanks. Okay, thank you.